Welcome to this course overview. We present Explorations in Particle Theory, taught by Cliff Burgess for the PSI program at Perimeter Institute in the 2015 to 2016 academic year. Across 14 lectures, the course follows three threads: dark matter, dark energy, and primordial fluctuations, taking you to the observational frontier where the standard model hurts the most. This is a graduate level topics course. Burgess frames it as cool topics in particle astrophysics rather than a traditional dark matter course. The audience is assumed to have taken quantum field theory and the standard model. Cosmology background helps, but a crash review is included. Its defining feature: it does not sell you any particular model, it teaches transferable tools instead. The standard model plus general relativity faces 5 observational puzzles: neutrino masses, dark matter, dark energy, primordial fluctuations, and baryogenesis. 4 of them come from particle astrophysics. This course takes 3 dark matter, dark energy, and primordial fluctuations as its vehicles, and keeps asking 2 questions. What exactly is the evidence, and how should theory respond? The course runs on 2 teaching threads. The overt one is tools. Learn to state problems in the language of effective field theory, identifying the relevant degrees of freedom and interactions, so you can test whether any new proposal breaks something that already works. The hidden thread is evidence. List the observations first, then judge the theory. That evidence, first habit, is the real takeaway. The course has 14 lectures. Lecture 1 is the overview. Lectures 2 through 10 form the evidence block, dark matter, thermal history, relic particles, and dark energy. Lectures 11 to 13 are the toolbox, the path, integral effective action, and renormalization with power counting. Lecture 14 wraps up, connecting dark energy with primordial fluctuations. Lecture 1 sets the stage. About 95% of the energy in the universe lies outside the standard model, roughly a quarter dark matter and 70% dark energy, both inferred purely through gravity. Burgess also surveys neutrino masses, primordial fluctuations, and baryogenesis, where the matter-antimatter asymmetry is only about 10 to the minus 10. Treat this lecture as the map for the whole course. Lecture 2 reviews the evidence for dark matter. Flat galactic rotation curves imply that the enclosed mass grows linearly with radius. Galaxy cluster masses are measured 3 independent ways: velocity dispersion, X-ray gas, and weak lensing, and they agree. The angular scale of the cosmic microwave background shows that space is flat, and flatness plus the measured matter budget directly requires non-baryonic dark matter. Lecture 3 is a cosmology crash course. Dust has essentially no pressure. For radiation, temperature is the only scale, so the energy density goes as temperature to the 4th power, and the pressure is 1/3 of it. Burgess introduces the sound speed 1 over √3 for photon gas and shows that during matter domination, density perturbations can be evolved with plain Newtonian dynamics. Lecture 4 covers structure formation. The moment of matter-radiation equality measures the total non-relativistic matter, and fits demand more than baryons alone. A perturbation grows linearly with the scale factor only after its mode enters the Hubble radius in a matter-dominated era. Modes entering earlier are stunted, so the shape of the power spectrum itself records how much matter there is. Lecture 5 takes MOND as the case study of modified gravity. An interpolating function inserted into Newton's law yields flat rotation curves and the Tully-Fisher relation in the low acceleration limit, with a constant of 0 around 10 to the minus 10 meters per second squared. 2 lessons. MOND unexpectedly gets some galaxy scale facts right, and its original formulation was wrong. It must be rewritten as an effective theory. Lecture 6 turns to thermal history. Relic particles are proof the universe was once hot, and their abundance today is entirely set by departures from thermal equilibrium. Equilibrium has a deep universality. Once the universe thermalizes, earlier history is essentially forgotten. So the real question is when and how each species fell out of equilibrium, decoupling, and freeze out. Lecture 7 builds the mathematics of detailed balance. Its foundation is the unitarity of the S matrix, not time reversal invariance. Requiring forward and reverse rates to agree is equivalent to matching phase space factors on both sides, including Bose enhancement and Pauli blocking. Taking logarithms turns these into additive conserved quantities, which is exactly why chemical potentials add and subtract across reactions. Lecture 8 applies the machinery. First, a subtlety. The universe is automatically electrically neutral, but a weakly interacting gas model needs an explicit electron chemical potential. The key formula is the freeze-out condition. When the reaction rate n times sigma-v drops to the Hubble rate, the species decouples, and its density then dilutes as the scale factor cubed. Weak cross-sections imply neutrinos froze out just before nucleosynthesis. Lecture 9 opens dark energy. Supernova distances versus redshift deviate from deceleration. The expansion is accelerating. Acceleration requires a component with sufficiently negative pressure, the simplest candidate being vacuum energy, with W equals -1. Supernovae, the microwave background, and the Hubble constant all intersect at the same point in the omega matter, omega lambda plane, a robust, redundant evidence chain. Lecture 10 confronts the vacuum energy problem. The observed dark energy density is only about 10 to the -3 electron volts to the fourth power. But zero-point energies diverge like the fourth power of the mode masses, dominated by high energy modes we cannot compute. Any large high energy contribution must cancel the known particles' contributions to absurd precision, the famous fine-tuning problem. Lecture 11 opens the toolbox. Criticizing the arbitrariness of the earlier one-loop estimate, Burgess introduces the path integral and Wilson's effective action. The generating functional W of J is defined by integrating over the field with an external source. W at zero source is the vacuum energy. Wilson's point: the low energy effective action is what remains after integrating out high energy modes, and the vacuum energy question must be asked in that framework. Lecture 12 cleans up terminology. The literature mixes effective action, quantum action, and 1PI action, which makes old papers confusing. The modern 1PI action, capital gamma, is the Legendre transform of W of J. Expanding it as classical plus quantum corrections yields the quantum-corrected vertex rules. Its computational statement is beautifully simple. Gamma is the generating functional of one-particle irreducible diagrams. Lecture 13 is renormalization and power counting. The core rule: if you keep only the 0th order in 1 over m, you need only renormalizable interactions. That is the conclusion of power counting. Burgess also sketches Polchinski's stronger proof from 1984, integrate out modes down to a scale lambda, differentiate, and you get an exact renormalization group equation for how the couplings flow. Lecture 14 ties everything together. After reviewing the dark energy story, it turns to primordial fluctuations. The tiny temperature variations in the microwave background are thought to be quantum vacuum fluctuations from inflation, a rare case of quantum fluctuations gravitating. Since inflation erases pre-existing fluctuations, what we see must be continually regenerated, stretched beyond the horizon, and classicalized. The quantum to classical transition remains an open gap. What do you take away from this course? 3 things: a checklist of the observational evidence for dark matter and dark energy, the analytical language of effective field theory, from generating functionals to power counting, and an evidence-first taste in theory. Watch and order lectures 2, 9, and 10 are the evidence highlights, and 11 through 13 repay a second viewing. Now, on to lecture 1.